Yeah, good afternoon. Let's start now. So, first of all, the convex optimization problem. Representation. So, one normal standard canonical form. So, suppose the optimization problem is like this: minimize some function g naught of x subject to gi of x less than equal to 0, where this I belongs to 1 to L, and another equality constant is Aj transpose X is equal to Bj, the affine function. Okay, so where this J goes from 1 to M. Okay, so so this is the canonical form. Now we can form equivalent for one form, that is the epigraph form. So number two. So number two epigraph form is to minimize. So here this g0x we need to minimize. So we'll introduce another variable like t here. So we'll minimize that variable, minimize t, and we'll include one more constant in the constant set. Okay, so here this subject to g0 of x uh, less than equal to t, and then everything else is same. So like gi of x is less than equal to 0, 1, 2. Now, so this is the epigraph form. So like one example professor has given for this form. So we can take that example. Minimize the infinite norm, and where the constant is subject to uh, x belongs to some set. So let us take this is a convex set, and this is also a convex function. So this optimization problem is a convex optimization problem. Now what should be the epigraph form of this? So now we need to minimize another variable t subject to infinite norm of x less than equal to t, and uh, x belongs to the convex set S. So this is the form, the representation of the convex optimization problem. Okay, now So now, last year I discussed uh, linear programming, LP problem, linear programming problem, and so for that case, I just discussed the KKT equations for the LP problem. But we can form a dual. So in the last two classes, I mentioned the first order necessary conditions and second order necessary and second order sufficient conditions for the equality constant case and for the inequality constant case, in both the cases. Okay. So for the first order necessary condition, in the case of first order necessary condition for uh, inequality constant case, we need to find out KKT equations. Five equations are there. So so that we need to find out, and then we need to solve those five equations, and then we'll get the candidate point, the local minimum point of the objective function. Now, for the convex function, we can find out the one dual optimization problem. So, if we can solve the dual optimization problem, the result of that, the solution of the dual optimization problem will be same as the primal optimization problem. So for the convex optimization problem, we can construct a dual optimization problem. So the procedure is as follows. So the dual problem. So maybe this dual problem and KKT equations both will be taught in normal lecture series in the next week, maybe I saw. So yeah, so this will help you to understand that lecture I mean better, maybe. So the dual problem of convex optimization problem. The primal optimization problem is to minimize fx. So this is the objective function and subject to hx equal to 0, where this h is a function from r power n to r power m. Okay, and is also 0, less than equal to 0. This is the inequality constant. This goes from r power n to r power p. So this is the primal optimization. So to solve the primal optimization problem, we need to find out the. So this is the primal optimization problem. So we need to find out the Lagrangian. Okay. So that is the procedure. So the Lagrangian function can be written as the Lagrangian function can be written as gx. Okay. So this is the Lagrangian function, and then the dual function definition. So then q of lambda comma mu So this is the dual function that is equal to infimum with respect to x of this Lagrangian, where so this is a dual function definition. So the dual optimization problem, the dual optimization problem is that maximize q of y, sorry, q of not y, q of lambda comma mu, lambda comma mu. Q of lambda comma mu maximize this subject to uh, this mu greater than equal to 0. Why this maximization is coming suddenly from the minimization? Because this is a concave function. That's why earlier it was a convex function. So this was the convex function, and this set was the convex set. So the summary is that solving the optimization problem, this optimization problem. So um, we can bypass this optimization problem through this optimization problem. Okay, so we can solve the second optimization problem, and the result will be as same as the first optimization problem. Okay, so this will help to solve the convex optimization problem quickly or easily. So that's why this dual optimization problem is coming. So so that's all. So what does it says that what does it say that this uh, so first we need to find out the Lagrangian function, this thing, Lagrangian function. So normally we need to I mean differentiate this Lagrangian function, and then finding the values of x, lambda, and mu, and then so that will be the optimal solution. So in this case we can find out this Lagrangian function. Then we can find out this q of lambda comma mu. This will be only I mean nothing but the infimum or minimum of this Lagrangian function with respect to x. Then we can maximize this q function subject to this greater than equal to 0. So this was the one condition from the KKT condition. That's why this condition is coming. So so that is the case. So that is the dual optimization problem. Now now we can revisit the linear problem. So the linear problem, last day I just uh, you find out the KKT equations for a linear program problem. Now we can here in this lecture we can find out the dual optimization problem of the linear program problem. Minimize C transpose X subject to X equal to B and uh, X greater than equal to 0. So this is the linear program problem. So now the dual optimization problem we need to find out. First we need to find out the Lagrangian. that is equal to C transpose. So Lagrangian is the fx actually. So fx plus lambda transpose hx plus mu transpose gx. So here fx equal to C transpose x. Fx equal to C transpose x. This is the fx, and then here hx will be what, b minus ax, because that is equal to 0, and gx will be minus x, that is less than equal to 0. That's why. So plus lambda transpose p minus ax minus mu transpose x. So this is the dual. So this is the Lagrangian. Now what should be the, so then we can so we can write down in a same equation like this actually. So C transpose plus C transpose minus lambda transpose A minus mu transpose into X plus lambda transpose B. Okay. Now so Q of lambda comma mu is equal to infimum of this Lagrangian. That is equal to, so if you find out, so here infimum is, you need to find out minimum of this function with respect to x. So if you put this equal to 0, or if you differentiate this thing with respect to x and put that value to 0, then we will get that this thing this thing is coming 0, this portion. So like this only. So this means so 1 second. So let me write down. So it is clear that L of Lagrangian x comma lambda comma mu has finite infimum with respect to x only if only if C transpose. So this thing is equal to 0 actually. That's what I'm saying. So C transpose minus lambda transpose A minus mu transpose equal to 0. Okay. So hence the dual function Q of lambda comma mu is equal to, put this thing equal to 0, this thing equal to 0, so then we will get lambda transpose B only. So lambda transpose B is same as B transpose lambda. So with the domain specified by the constant C transpose minus lambda transpose A minus B, sorry, minus mu transpose equal to 0. So hence the dual optimization problem is maximize B transpose lambda. So this thing, this is the maximization problem. So maximize this thing with subject to C minus A transpose lambda minus mu is equal to 0 and mu greater than equal to 0. So this thing is greater than equal to 0, this mu. Okay, so in another way we can find out, or we can write down in this way also. Minimize minimize. So this is a maximization of this. So minimization of minus, we can write minus B transpose lambda subject to the C minus A transpose lambda. So this mu is greater than equal to, this is greater than equal to 0. So then this thing is less than equal to, so once again, this thing, so you can write down in this way. So A transpose lambda minus C less than equal to 0. So this is the dual optimization problem of the linear program problem. Okay. So you can solve this problem by the KKT equations, and maybe this can be easy to solve than the, this can be easier to solve than the triangle optimization problem. So that's all for the dual optimization problem. Now we'll go to some topics what professors has taught. Professor has taught, that is the compressive sensing. So the compression sensing problem is that, so suppose we have very less number of measurements. Suppose y is the measurements or observations or measurements. Okay, so y is the measurements. So we need to find out. So this is the system model. So this matrix. Suppose one matrix is there, y into x. Okay, so and this dimension. So this is suppose one vector of high dimensional vector. So this is a system model. Suppose we have very less number of measurements, less measurements. So now we need to find out this x using this system model. So that is possible only if this x is sparse. Sparse means there will be so many zeros in this x. Then we can find out x using this system model. Sparse vector. So this x is a sparse vector. Then only we can find out uh, x from this system model, where this y is, this measurement is very less actually. Now so that means in mathematical form, so this phi is called the sensing matrix of dimension m cross n. Okay, size is m cross n. So then what is the m? M is the number of measurements. Measurements. That means this y belongs to Y is a m-dimensional vector, and n is the uh, number of unknown variables. Unknown variables. That is the this x belongs to r power n, and this x is the sparse vector, and this m is the much less than n. That is what I am saying, that measurement is very less. Okay, and this x is the sparse vector. Okay, so now there are many procedure to find out the sparse vector. So now the optimization problem is sparse recovery problem is that. So this the x is called the sparse vector or sparse signal also you can write down. Okay, this is also called the sparse signal. So then so this finding out x from this system model is called the sparse signal recovery problem. So the sparse signal problem. So problem is that, so the optimization problem is that we need to minimize L0 norm. L0 norm is the number of non-zero elements in X actually. So that is what sparse signal is. We need to minimize the L0 norm subject to is subject to y equal to phi x. So this is the sparse signal recovery problem, optimization problem. Now, sorry. So so but this function is that is a highly convex function. Sorry, highly non-convex function. So it's very difficult to solve this kind of optimization problem. So the thing is that here this optimization problem has the combinational complexity. So that means uh, this algorithm can be 1, 2, 3, 4. We need to, I mean, so in this combination there will be so many combinations. We need to check for every combinations what uh, for which value this is the minimized subject to this constant. So this will be combinational complexity. There will be combinational complexity, and This problem is called the NP hard problem. So that's why we can't solve this in practice. Okay, so there will be so that's why this problem we can't solve it directly. One greedy algorithm is that orthogonal matching pursuit. So matching pursuit algorithm is the greedy algorithm. So orthogonal matching pursuit is the so this is also named as OMP. This is a greedy algorithm. So the so we need to minimize actually same thing L0 norm only, but there will not be any optimization problem. So we can't say that the output of this algorithm is the optimal solution. So that is not optimal. That will be some iterative and low complexity based algorithm. So but that is not the optimal. So then subject to y equal to phi x. Sorry. So this phi has so many columns. Phi one, phi two. So this is the tilde dot phi n into x1, x2. So this is the m cross n matrix. Uh, so this is the optimization problem. So we will solve this. So the algorithm is as follows. So I will not go through the all details. Professor has already taught this thing. I will just write down the algorithm. So algorithm is first is that someone has assessed me this how to find the optimal transmit and receive informing vectors. Yeah, I'll do that thing in the problem solving session.
Okay.
In the rest, yeah. So algorithm is that so this R is the residue. R is equal to Y. So first we will introduce one vector, one variable R. R is called the residue. So this is the residue. Residue will take that is the same as Y. Then one set will this is the support set. Okay. So suppose so this is the support set. Support set means that that will contain uh, one second. So support set is the indices of those of the entries of X actually. So X is the n-dimensional vector x1 x2 dot xn. So the indices are from 1 to n. So S will contain all those non-zero indices. Like out of this n, only p number of suppose out of 100, n is equal to 100. Only two entries are non-zeros. Okay, so then S will contain only those entries. Suppose second entry and 10th entry. So this S will contain 2 comma 10. Okay, so and that's why at the beginning I am. So S is a null set at the beginning. So after the algorithm, it will contain two elements. So then, then we will take one matrix that is the A is also a null matrix. Now I am taking. So after that, so now we'll start the loop actually. So now we do what? So we need to find out one lambda that is equals to R transpose this phi, in absolute of this thing. So R transpose phi means that R is the residue. At the beginning, it is the Y. So then we'll find out Y transpose phi. That means that means the correlation between the Y and the columns of phi actually. So this is the uh, uh, so this correlation vector I am calculating. So this is the lambda vector. Okay. So R transpose phi we are calculating. Now we'll find out the maximum. So now suppose this is the value and in this index, value and index of a maximum of lambda. Okay, so lambda is a vector. So we'll find out the position and the value of the maximum correlated value actually. So that means index will show that in this position the correlation is the maximum. So that's the index. So and value will determine the correlated value. So then S is the set. So S will take earlier S and semicolon this index. Okay, so this index. So then it will take the index of maximum correlated element or projected element. So this R transpose phi is the determining the correlation or projection. So projection of R onto the column of phi. Okay. So then is A is calculated as A comma phi of this index. Okay, only those column will take that column we will take. Then we will find out x x equal to pseudo inverse of so pseudo inverse of A into Y. Okay, and then another vector. So then R is the residue will calculate. Residue will be Y minus already this X is determined, so we can eliminate that portion from the Y. So Y minus A into X. Sorry, phi into X. Not phi. A into X. Sorry, A into X. Okay. So this is the then in while this will continue. One second. How to write the loop? Is R residue of this norm of R is something less than equal to uh, greater than equal to some 10 power minus 3. So I mean so this is the end of the loop. So so this is the loop actually. We'll run this loop till this R converges. So this R is the residue. So this R converges. So this is the loop. So this is the one procedure to find out the sparse vector or sparse signal. But this is not the optimal. So similar. So we can find out the or via another optimization problem also we can find out the sparse signal. So that optimization in that optimization we can minimize the L1 norm instead of doing minimization of L0 norm, because L1 norm is the convex function but L0 norm is not a convex function, that's why. So via L1 norm minimization. So the problem is as follows: minimizing similarly instead of doing L0 norm, we will do L1 norm here. So x1 and then subject to y equal to phi x. So that this will also give or provide identical sparse vector x, and L1 norm is convex. Okay, so this is the optimization problem. Now the epigraph of this optimization problem is that so epigraph is that suppose this is a one is a vector one transpose t and then subsume this is the sorry, so you can minimize on transpose t subject to minus t less than equal to x less than equal to plus t and y equal to yx. So this is the epico problem. So how this is coming, professor has already taught in the class. That's why I'm not going into the details. So this is the linear program LP problem. We can solve that. So you can solve that thing efficiently. Now okay, the time now. So now we can go to some sample problems. First one is that consider okay, so orthonormal vectors. Suppose one question is that consider vectors 1 minus 1 1 and 0 minus 1 1. Now find out the orthonormal vectors corresponding to them. So in the assignment you will get some other vectors maybe. So I am changing the vector. So the solution is that simple. So we can use the Gram-Smith orthogonalization problem. So in the first class I told that thing. So what should I do? So I will take so the first vector is the uh, so first vector is x1 is equal to 1 minus 1 and 1. So now what is the norm of x1? For the orthonormal vectors, norm should be 1, but here the norm is the yes, L2 norm. L2 norm is 1 plus 1 1 square plus minus 1 square plus 1 square, that is equal to root 3. So then we'll find out another vector b1 that is equal to this x1 divided by norm of x1, that is equal to 1 by root 3 1 minus 1 1. Okay, so then another vector x2 was 0 minus 1 1. Okay, 0 minus 1 1. Now what is the norm of x2? So now okay, not norm of x2. So now, so this is another vector x2. So now we'll find out the projection of this x2 on this vector v1. Okay. So that means we'll find out the inner product of v1 and x2. That is means x2 transpose v1. We'll find out is equal to x2 transpose is this 0 minus 1 1, and v1 is 1 upon root 3 minus 1 by root 3 1 by root 3. So that is equal to minus minus plus 1 up 1 by root 3 plus 1 by root 3. That is equal to 2 by root 3. So this is the projection. So that means now we have to eliminate that projected value from the original vector. So that is, so suppose let's take u another vector. U is equal to this x2 minus projection of um, x2 onto v1, then v1 is the normal unit vector. That is equal to x2 was the 0 minus 1 1 minus 2 by root 3, 1 upon root 3 minus 1 by root 3 1 upon root 3. That is equal to 0 minus, so minus 1 minus 2 by 3 minus 2 by 3, and then plus 2 by 3 plus 1, sorry, not minus 1 plus 2 by 3, so 3 minus 2 is the 1 by 3, then 1 minus 2 by 3, so minus 1 by 3. 2 by 3, 0 minus 2 minus 2 by 3, then minus 1 plus 2 by 3, so 1 by 3, 1 minus 2 by 3, 1 by 3, 1 minus 2 by 3, 1 minus 2 by 3. This will also be plus minus 1 plus 2 by 3. So this is the minus 1 plus 2 by 3, 1 by 3. Okay. So so this is the, then what should be the so no, orthogonal vector that is equal to u divided by norm of u. So then norm of u is equal to over 4 by 9 plus 1 by 9 plus 1 by 9. It is equal to 4 5 6. So root over 6 by 9. That is equal to root 6 by 3. So 3 by root 6 into this thing, minus 2 by 3 minus 1 by 3 1 by 3. That is equal to minus 2 by root 6 minus 1 by root 6 plus 1 by root 6. This is the another vector v1 and another vector. Oh, this is the v1. So then we can change this to u v2 actually. This is the v2. So this is, so we can find out the dot product between them. So 1 by root 3 minus 1 by root 3 plus 1 by root 3 here, minus 2 by root 6. So 1 by root 3 into minus 2 by root 6. So that is the minus 2 by root 18 minus minus a plus by 1 by root 18 minus minus a plus 1 by root 18. 0. Okay, so this is the orthonormal vectors. Then the second problem is that maximize A transpose AX subject to norm of X is less than equal to 1. So X transpose AX. So then, so we need to find out these things. So how to find out? So first we need to find out the Lagrangian. Lagrangian is L is equal to X transpose AX minus lambda into sorry plus lambda into X transpose X minus 1. Okay, now we need to differentiate this thing with respect to X. That is equal to 2AX 2AX plus 2IX equal to 0. I is the identity matrix. Then, oh, sorry. So this is the just maximization problem. Then we can convert this to uh, minimization problem. So we can minimize is minus of X transpose X subject to norm of X less than equal to 1. So then this will be minus. So then this is the minus. So then we can write down this way: X equal to X lambda. Sorry, one lambda should be there. Lambda X. So here this we can write say that this lambda comma X is the eigenvalue and eigenvector pair of A. Okay. So then X transpose X is equal to, so suppose, so here X is the eigenvector. X is the eigenvector, then we can write down this thing as same as lambda of mod of X square. This is equal to X transpose X equal to lambda X, then lambda mod of X square. Okay. So we need to maximize this thing. Okay. So that means so this is the eigenvector. That's why it's always greater than equal to always greater than 0. No, always greater than 0. So this lambda is the eigenvalue. So maximizing this thing is same as maximizing this lambda. That means we need to find out the maximum. We need to maximize the eigenvalue of A. So that means the solution will be maximum eigenvalue of value of A equal to lambda max. Okay. So so this is the solution. Similarly, suppose if someone says that minimize this X transpose X, that will come to lambda mean, minimum eigenvalue of A. So that is a similar problem. Then the next question is, suppose n is a vector n1 to n. Suppose the n dimensional vector, n dimensional vector. Okay. So and ni, each element in n is the IID. independent and identically distributed normal distribution. Suppose this the mean is mu. So let's simplify it. Let's take mean is 0 and variance is sigma squared. Okay. Then what should be the summation of Ci Ni I equal to 1 to n. So suppose this is another random variable, that is the n tilde. So this what should be the distribution of this? So the solution is that this is the linear function of this Ni. So linear combination of this Ni. So that's why it will also be a Gaussian distribution. So that's a property of Gaussian distribution. So Ci Ni that is also a Gaussian distribution, also normal distribution. But the mean and variance we need to calculate. Suppose mean is mu and variance is sigma. Sorry, variance is sigma 2 square. Let us take now we can find out mu as this function of these things, and sigma 2 square also find expansion function of these things. So how to find out? So suppose expectation of n tilde. Suppose expectation of n tilde is equal to ci summation expectation of ni. Okay. So now expectation of ni is equal to 0 because the mean is 0. That's why it's also 0. So then we can write down mu is 0. Okay, so this is the 0. And what should be the sigma 2 square? Sigma 2 square we need to find out. Sigma 2 square is equal to expectation of n tilde transpose. But here all are scalar. Okay, all are scalar. So then we can square this thing. But let's take transpose also. Okay, n tilde that is equal to expectation of summation of ci ni transpose summation of ci ni. So that means all are scalar, so no need to write down the transpose then. So it's same as I equal to 1 to n ci ni multiplied with j equal to 1 to n cj nj. Okay, so that is same as okay. So now due to this IID those distributions, so expectation of ni and nj will be 0. Sorry, will not will be expectation of ni into expectation of nj as they are independent, and these are zeros. Mean is 0. So this also 0. So that's why. So as their IID and I not equal to j actually. Okay, and expectation of ni squared is equal to sigma squared is mentioned above. So then here ci for I not equal to j it can so the thing is that here this will be uh, ci when I equal to j that will be non-zero, so that's why it will be summation of there will be one summation only I equal to 1 to n ci square ni square is equal to summation ci square expression ni square equal to sigma square. So sigma 2 square equal to summation ci square sigma square. Okay, so this is nothing but it is also following the normal thing actually. Suppose this x is a one random variable okay, which has a variance sigma 1 square, and y is also another random variable sigma 2 square, then what should be the variance of ax plus by? Okay, that will be the a square sigma 1 square plus b square sigma 2 square. So that's why it's following this thing, this same rule. Just I have solved it in different way. Now, this is the one question. Another is the fourth question. For the compressive sensing. So it's just a multiple choice question for the compressive sensing problem. Which norm should be minimized? So question first option is L0 norm only. Second is L1 norm only. Third is L0 and L1 norm both. Fourth L infinite norm. So the solution is this, right answer is this L0 and L1 norm. So if we minimize L0 and L1 norm, then we will get the sparse signal. Okay, and so then fifth question is that so consider the MIMO case. So one was asking that for the MIMO case, how to find out the transmit and optimal transmit and receive beamforming. So in the class, Sarah has taught how to find out those things. So like that. So consider MIMO case, but that is also assignment problem actually. Still, as he has mentioned in the class that how to find out the optimal transmit beamforming vector, that I can write down here. Okay, consider the MIMO channel age. So optimal uh, TX and transmit and receive beamforming vector. So the solution is that, so the I will not go through the detailed solution. He has proved that. So optimal transmit beamforming is that optimal transmit beamforming is the eigenvector corresponding to the maximum eigenvalue of corresponding to the maximum eigenvalue of H transpose H. Okay, H transpose H. Now optimal receive beamforming is equal to, so this will also be a similar thing, eigenvector corresponding to maximum eigenvalue of some different matrix that I will not mention specifically here. So you can just the same process you can, that is the exactly question from the assignment question, that's why. So okay, this matrix can be different or same, can check it. So so that's all for the question. So now, yeah, that's all for the for today. So I can revise this thing again once more, and then we'll stop. So
Sir,
so
what about the receiver beam forming vector? How to calculate?
yeah, for the receiver beamforming vector, it will be actually the question is same from the assignment. So directly I can say, I can't say here. Here means now actually after the assignment I can say. So suppose the optimal transmit beamforming is eigenvector of the maximum eigenvalue of H transpose H. So similarly there will also you will get eigenvector corresponding to the maximum eigenvalue of other matrix, that is H transpose H or some other matrix. You can check it. Okay.
Okay, sir.
Yeah. So yeah, then I can revise this thing. So Uh, so this is the convex optimization problem representation. So this is a canonical form and epigraph form. So so just one, I mean, so just one in one another variable t is introduced here. Then we can and then one another constant is also introduced in the constant set. That is the g naught x less than equal to t. Then this is the example of infinite norm, maximizing the infinite norm. Okay, so suppose so in this way epigraph form we can convert the infinite norm to uh, LP linear program problem. How? Because he has already solved it. Equivalent problem is so this is the equivalent problem. One second. Not this one, not this one. Okay, L1 norm. So he transformed the L1 norm to linear program, minimizing the L1 norm to linear program. Uh, okay. So here also infinite norm is converted to uh, epigraph from through the epigraph from here infinite norm is converted to this minimizing t. So this is uh, as similar as a linear program kind of problem. So we can convert this thing. So epigraph from will help us to solve the problem easily. The dual problem or convex optimization problem is that so duality may be taught in the next week maybe. So this session will help you to understand that duality better. So the dual problem or convex optimization problem is that suppose this is a primal optimization problem minimizing fx subject to these constants. One is equality constant, and another one is inequality constant. Then we need to find out the Lagrangian function L of x comma lambda comma mu, where L this Lagrangian is equal to fx plus lambda transpose hx plus mu transpose gx. Then we need to find out the dual function. Dual function is the another function which will be independent of x, that will be only depending on lambda and mu. So this is the meaning finding the this is the infimum of Lagrangian with respect to x. Okay, so then dual optimization problem is that maximizing that dual function subject to this mu is greater than equal to 0. So this is coming from the KKT condition. That's why. So KKT condition I taught in the last class. In sir will also professor will also taught in the next week maybe. We'll understand that thing better. So linear program result is that linear program revisit. So our last day I taught that how linear program is constructed and how it is solved through KKT equation. But for that case you need to solve those five equations properly. Then okay. So but for the linear program or program case you can find out the always find out the dual optimization problem, and you can solve the dual optimization problem also. So that means the solution of the dual optimization problem and solution of the primal optimization problem will be same. That is the strong duality condition. That is the one duality condition, the solution will be same. Okay, so so one second, so I can write down the strong duality condition. So this is a dual equivalent problem of the linear program. Uh, okay, linear program optimization problem. Strong duality relation I can write down here. Dual problem, linear program. Here. Strong duality relation. If x star and satisfy security conditions. X and Y solve the primal and dual problems respectively. Respectively, and the values of the objective function at the solution points are equal. So that means that the so in other way the solution of the dual optimization problem will be as same as the primal optimization problem. That is the summary of this strong duality relation. So this is a linear program problem, and then this is the dual problem of the linear program problem. Then the compressed sensing case. So we need to find out the sparse signal. We need to recover the sparse signal from this measurement model y equal to phi x, where the number of measurements is very less and the signal x is a sparse signal. That means there will be very few non-zero elements in the x. Uh, so this is the sparse equal problem. So first, so the problem is that minimizing the L0 norm, but that is not that is a complexity that is uh, computationally intensive problem. So that's why we can other way we can do that. One is the greedy algorithm, that is the orthogonal matching pursuit algorithm. Another one is the minimizing the L1 norm. So finding so using the greedy algorithm, that is the OMP algorithm, that will not find out the optimal solution. That is just a greedy algorithm. It's just a less computationally expensive, very uh, simpler and efficient way, not efficient, very simpler way to do to find out the sparse signal. So that's why it's named as a greedy algorithm. But this is not the optimal solution. So this is the process. We need to find out the residue in each. So this is the loop. This is the loop actually. So in the first, here we will find out the. So in each iteration, we will find out correlation between the residue R and measurement matrix phi. What is the residue at the beginning? It will be Y itself. Then after that, we'll eliminate some portion which has already estimated. We'll eliminate that portion from the receive vector Y, and then we'll find out the residue R. Okay. This is the uh, problem. Okay. So this residue. Okay. One second. So this thing can also be eliminated, and this thing, so we can find out the so like that way. So we can x new. So suppose what will be the convergence criteria? Suppose x is the sparse signal, so x new is the minus x old, and then norm of these things is less than equal to. So if this is less than equal to minus 10 power minus 3, then we will not go to like that actually. Not minus 10 power minus 3, some other epsilon that is very less. Then we will perform this case, this process. So then minimizing the L1 norm also we can find out the sparse signal by minimizing the L1 norm. So that is becoming a LP problem that can be solved efficiently. Then I discussed 5 problems. One is the how to find out the orthonormal sets, and then correspond to the independent orthonormal set of vectors correspond to the independent set of vectors. Then we are maximizing this x transpose. So this operation problem is solved here, x transpose x. And then how to find out the mean and variance of linear combination of the noise elements ni. And then So this is the comprehensive sensing. So L0 and L1 norm we can minimize. And then for the MIMO child, the transport beamforming will be the eigenvector corresponding to the maximum eigenvalue of H transpose H, H Hermitian H. So yeah, that's all for the day. Thank you for joining. If you have any question, you can ask me, or you can stop here. Model question of final test. Okay, okay. Yeah. Sorry, I didn't search actually. Sorry for. Thank you for reminding me. So I'll ask. Okay, and I will try to share. Okay. I don't have any model question. I need to ask.
Okay, sir.
Okay. Thank you. Thank you for joining.